Hey, welcome back. Let's try to solve this example. This is a single unit material balance problem for mixing process. Two aqueous sulfuric acid solutions containing 20% by weight sulfuric acid given specific gravity and 60 weight percent sulfuric acid with a different specific gravity are mixed to form a 4 molar solution. The question is, letter A, what is the mass fraction of sulfuric acid in the products? And letter B, we are to determine the volumetric flow rates of the two feed streams that will produce 1,250 kilograms per hour of the products. The first step in solving this problem is to first identify what the process is. So we have mentioned earlier that this is a mixing process, right? We are trying to mix a weaker sulfuric acid solution with a stronger solution, and a mixing process requires a mixer as its unit. So for a second step, after identifying the process, is to draw the diagram. Let's draw our diagram. I'm going to draw a simple block flow diagram for a mixer. And we have two feed streams coming in, right? This is your 20% and your 60% strength of the solution. And then, of course, after mixing those, you would end up with a product that has a concentration in between the 40% and 60%. Sorry, the 20% and the 60% solution. So let me label my streams. I will call this stream letter A. This is my 20% by weight sulfuric acid solution. Of course, since these are aqueous solutions, the balance of this will be 80% water. My second inlet stream, I will call this stream B. This is my 60% by weight sulfuric acid. The balance of this is 40%, and that is water. By the way, if you cannot tell, I'm writing this as we speak. My product, my one outlet stream, I'll call this my stream P, or the product. This is supposedly a 4 molar solution of sulfuric acid. However, we cannot leave this simply as 4 molar because we cannot perform our material balances with a molar concentration. Typically, we have to convert everything to percent by weight or percent by mass in order for us to do the overall material balance and the species balances. Now, if you take a look at what's required for letter A, we are looking for the mass fraction of sulfuric acid in the product. We can actually already determine this by converting molarity to a percent by weight. So let's do that side calculation first. Let's consider stream P. If we say that the concentration in stream P is 4 molar, that means that you have 4 moles of H2SO4 or sulfuric acid for every liter of the solution, because the definition of molarity is moles per liter, right? Now, it's necessary for us to set a mini basis. We usually call this a mini basis, or you can also call it a different thing. But basically, this mini basis would just be applicable for stream P. It will only be applicable for this small calculations that we are doing right now to convert molarity to percent by mass. And typically, a good or a convenient mini basis for this one is the denominator of our concentration expression. The denominator is liters of solution. So I will say that my mini basis is 1 liter of the solution. If you have 1 liter of the solution, that also means that you have 4 moles of H2SO4. So that's the reason why 1 liter of the solution is a very convenient basis, because the molarity is already equivalent to the number of moles of sulfuric acid. Now, your 1 liter solution needs to be converted to mass, as well as the 4 moles of sulfuric acid. Remember, we are trying to convert everything to percent by mass or percent by weight. So let me start with the solution. My 1 liter solution can be converted to kilograms simply by using the given specific gravity of the 4 molar solution. So let's focus on this part for a bit. if your specific gravity is 1.213 and if our reference substance is water at its densest, that's typically 4 degrees Celsius, the density of water at that point is very, very nearly equal to 1 kilogram per liter. Therefore, if that's your basis, the specific gravity can be converted to a density that is numerically the same. I can say that the density of the 4 molar solution is 1.213 kilograms per liter. Again, I'm using the basis of water at its densest point of at 4 degrees Celsius with a density of 1 kilogram per liter. And this is the value that we need to convert your liters of solution to kilograms of solution. So let me multiply this with the density of the solution, 1.213 kilograms per liter of the solution. The unit of liters will cancel, and you will see from our calculation. Let me calculate. Sorry, no need to calculate. That's just 1 times 1.213. So that is 1.213 kilograms of the solution as well. Notice our calculator here up top, so you will be able to see my thought process in the calculations as well. So you have 1.213 kilograms of the solution. This is already the total mass of your solution in the product using our mini basis of 1 liter of the solution. Now let me convert the 4 moles of sulfuric acid into kilograms. The molecular weight of sulfuric acid is around 98 grams per mole. So I'm going to multiply this by 98 grams of sulfuric acid per mole of sulfuric acid. This will cancel out. But then I need these values to be in kilograms. So I'm going to add another factor here that for every 1,000 grams, you have 1 kilogram. So that we will know exactly the mass in kilograms of the sulfuric acid. Now we need the calculator. So that will be 4 times 98 divided by 1,000. So as you can see here, we simply multiply the moles with the molecular weights and divide that by 1,000 to convert that to kilograms. So I'm getting 0.392 kilograms of sulfuric acid. Now let's go back here. If your solution weighs 1.213 kilograms and the sulfuric acid that is contained in that solution weighs 0.392 kilograms, that means that the difference between these two values is the mass of water. To simplify that, so let me do this in a table form. I have here my 2 components. Our 2 components are sulfuric acid and water, right? This is still in the product. Let's list their mass in kilograms. So I determine that the mass of sulfuric acid in the solution is 0.392 kilograms. And then for water, you will simply subtract 0.392 kilograms, which is the mass of sulfuric acid, to the mass of the solution. So let me do that here. That will be 1.213 minus 0.392. That's 0.821 kilograms for water. But the most important thing here is that if we get the sum, or if we get the total mass of the solution, you should still be getting 1.213 kilograms because that was according to our mini basis of 1 liter of solution. 1 liter of the 4 molar solution weighs 1.213 kilograms, so your total mass should still be 1.213 kilograms. Okay, and it is from this one, it is from these calculations that we can finally get our percent by weight or percent by mass. For the percent by weight, you simply get the mass of the component and divide that by the total mass. So for example, for sulfuric acid, that would look like 0.392, which is the mass of sulfuric acid. and divide that with the total mass, 1.213 kilograms. This is now what we call a mass fraction, right? Mass fraction, if you want to convert that to percent by weight, simply multiply this by 1,000. So this is 32.32% by weight for sulfuric acid. For water, you can do the same thing. You can simply change your numerator to the mass of water, which is 0.821. And you will get here the percent by weight, the mass fraction rather, of water. And to convert it to percent by weight, we multiply by 1,000. So this is 67.68%. But conversely, once you get the mass fraction or the percent by weight of sulfuric acid, you can simply subtract that from 1 or 100% to get the equivalent percent by weight of water. Okay? Nonetheless, if you take the sum of the percent by weights of the components in a mixture, it should always be 100%. Now, granted, sometimes there might be rounding off errors in which you would get a little bit more than 100% or a little bit less than that, but one thing's for sure, we have to make sure that it's very nearly 100%, okay? To make sure that we are consistent in our calculations. So these values right here are exactly what we need in order to proceed with our calculation. So right now, I can pick up these two values of the percent by weight and add them into our diagram here. By the way, I forgot that this is a mixer. So our product contains 32.32% sulfuric acid and 67.68% by weight of water. Now remember that whenever you set a mini basis, the only things that you can carry over to your main solution are your percent compositions that we were able to calculate earlier. Okay? I cannot take the 1 liter solution used as mini basis and have that in our main problem here. Okay? The mini basis only exists in this part of the problem. Now our diagram is actually complete. So if you go back to the problem, you were already given the percent by weights of both sulfuric acid and water in the two feed streams. In the product stream, we just got that coming from our side calculations here. We have answered letter A. To answer letter A, what is the mass fraction of sulfuric acid in the products? It's 32.32% by weight, but in terms of mass fraction, that is 0.3232. That is our answer. Okay, I hope that you get the difference between a mass fraction and a percent by weight or percent by mass. Okay, the difference, it's just a little bit of a difference, but in some cases, it's best not to be confused with that difference. Let's answer letter B. Determine the volumetric flow rates of the two feed streams that will produce 1,250 kilograms per hour of the products. Now we were given a value for the products. It says on the problem that we have 1,250 kilograms per hour of our mixed product here, and I want to determine what are the flow rates of A and B. Now, the flow rates that we are looking at, or we are looking to find, are volumetric flow rates, but what we are able to get from the material balances are mass flow rates, because remember that material balances are mass balances. They are not volume balances. Okay, so let's first perform the mass balances and then later on convert the mass flow rates to volumetric flow rates. Let's proceed with this diagram. I'm going to set my basis. My basis is for every 1 hour of the operation. Granted that my flow rate for the product is given as kilograms per hour, for every 1 hour of operation, you get 1,250 kilograms of the products. Now we can proceed to the main events, which are the material balances. The OMB, or the overall material balance, is simply a sum of the inlet, and that's equal to the sum of the outlet masses. This is a steady state process, or we are assuming that this is a steady state process, so there is no accumulation in this problem. So my OMB will be A plus B is equal to P. A and B are our two feed streams. P is our product stream. I know the value of P, so I'm going to substitute that here. It becomes A plus B is equal to 1,250. And do take note that all of the terms in this equation are in kilograms. They are in mass basis. Okay? According to this equation, we have two unknowns. That's A and B. So let's develop another equation to solve the two unknowns. And that would come from a component balance. Notice that we have two components, sulfuric acid and water. You can pick either of those. Your calculations would still be the same. So let's pick sulfuric acid. I'm going to perform the sulfuric acid balance. How do we write that? How much sulfuric acid is in your stream A? That's simply 20% of the entire stream A. So you can write that as 0.2 times A. Plus, how much sulfuric acid is in stream B? That is 60% of B. Or you can also write that as 0.6 B. On the other side of the equation are your output, or is your output. In the product stream, we know that there is 32.32% sulfuric acid, writing that as 0.3232 times P. But you already know the mass of the product, right? The product is 1,250 kilograms. So you can substitute that there already. Now we have our two equations right here. The first equation comes from my OMB, and the second equation comes from my sulfuric acid balance. You can solve those two equations with two unknowns directly on your calculators. Or if you're not allowed to use calculators, you can perform substitution or elimination methods to determine the values of A and B. But for us, we can do that straight in our calculator right here. Okay, so let me do those calculations. That's two equations, two unknowns. I'm going to use X. So let me write that here. I'm going to use the variable X as proxy for A and Y for B, so that so that you can follow that in my calculations here. So to calculate, for my first equation, that will be X plus Y equals 1,250. That's our first equation, right? This one. My second equation is 0.2 times X plus, or let's just use 0.2X plus 0.6Y equals 0.3232 times 1,250. This is our second equation right here, already plugged into our calculator. Okay, now the result of this is this one. My X has a value of 865 and my Y has a value of 385. So we can write that here. A is the same as X in our calculations, so that is 865 kilograms, and B is 385 kilograms. Now, going back to your basis, remember earlier we said that the basis was 1 hour of operation. So this translates to flow rates of 865 kilograms per hour and 385 kilograms per hour. These are the flow rates of stream A and stream B. Okay, there's a difference between mass and mass flow rates. So in the overall material balance, what we are balancing are masses, but what we are reporting as answers are mass flow rates using the basis of 1 hour. Okay, so you can already see the importance of setting a very good basis, because when you if you choose a different number for this basis, you might have to perform additional calculations to determine the mass flow rates. Okay, but for us, we chose 1 hour of operation, so it's just directly the mass is numerically the same as the mass flow rate for 1 hour of operation. Okay, now read again what is being asked for letter B. We are to determine the volumetric flow rates of the two feed streams. What we have calculated right here are mass flow rates. So there still needs to be a conversion from mass flow rates to volumetric flow rates before we can declare our final answers. Now notice again in the problem that you're also given the specific gravities of the two feed streams. So your 20% by weight solution has this specific gravity, and based on our previous experience, we can simply say that the density of the solution is 1.139 kilograms per liter for the same basis of water at its densest. And for the 60% solution, this given specific gravity equates to a density of 1.498 kilograms per liter. These are the densities that we're going to use to convert from mass flow rates to volumetric flow rates. Let me do that here. So let me do it first for stream A. We know that stream A has a mass flow rate of 865 kilograms per hour. I'm going to do it this way so that you can see the cancellation of units. Now, do we need to multiply or divide by the density? That depends on what unit you are trying to cancel. I'm trying to cancel kilograms. So I'm going to place that in the denominator. So apparently, we are going to divide with the density. So stream A has a density of 1.139 kilograms per liter. And kilograms will have to be cancelled. Take a look at the remaining unit. It's liters per hour. That's a volumetric flow rate. Calculating. That is 865 divided by 1.139. That is 759.44 liters per hour. That's a volumetric flow rate. Do the same for stream B. With the mass flow rate of 385 kilograms per hour, we divide as well with the density, but the density of stream B is different. It's 1.498 kilograms per liter. Kilograms will cancel, and you can calculate. That's 385 divided by 1.498. I'm getting 257 liters per hour. Now, depending on the required level of rounding off, then you can simply revise your final answers with the required number of decimal places. So for this problem, these are your volumetric flow rates of stream A and stream B. That is it for this problem. If you have any questions, feel free to drop them in the comment section below. Thank you for listening, and I'll see you in the next one.